Swayam Prabha. Digital India. Educated India.
So now we come to another problem in NP called SAT. Right? SAT is short for satisfiability. So basically it is a Boolean formula and we are asking whether it is satisfiable. Right? So what does the Boolean formula contain? It contains variables, let's say x1, x2, x3. There are negated variables, which is x1 complement, x2 complement. Right? So both of these variables and the negated variables are sometimes together called literals. Literals are both xi, x1, x2, x3 and so on, and x1 complement, x2 complement, etc. Right? So both variables as well as the negated variables, and they are connected using two logical things, logical connectors, right? So one of them is AND, which is depicted as this, depicted like this, like an inverted V or an A without a bar, and the other one is OR. So OR is depicted like a V. It's exactly like a V, right? So one example is this, this Boolean formula given here. So let's say this is phi, right? So is there a way to assign values to x1, x2, x3? So there are only three variables, x1, x2, x3, such that this whole formula phi evaluates to true. So I want to make this formula true. Is there a way to assign x1 and x2 values, x1, x2, x3 values, so that the whole formula evaluates to true? Let's see. So so it's an AND of four things. So first the AND of x1, then x1 complement or x2, then x2 complement or x3, and then x3 complement. So there is an AND of x1, which means x1 should be true, right? Maybe I'll write it here. So x1 should be true, because if x1 is false, the whole thing is false, right? Because it's an AND of four things, right? So x1 should be true. But then if x1 is true, then x1 complement is false, right? So now I want this part to be true. x1 is true means x1 complement is false. So which means x2 has to be necessarily true. Otherwise this part is going to be false. So x2 also has to be true. Now we know x2 is true, right? Which means x2 complement is false. So now I want this clause x2 complement or x3 to be true. Now it necessarily means that x2 is true. So the only way phi is satisfied is if x1 is true. And now I want to satisfy this clause, the second clause. So the only way phi can be satisfied is if the second clause is true. But we know x1 has to be true, so x2 also has to be true. And now since x2 has to be true, the third clause has to be true, x3 also has to be true, right? So from the first three clauses, what we gather is that x1, x2, x3 all has to be true for the phi to be true. But let's see. So the final clause is just x3 complement, right? But then we already saw that x3 has to be true. So this has to be false, which means whatever we try, so we got that x1, x2, x3 has to be true. But then x3 has to be false. But then x3 has to be assigned either true or false. It cannot have both assignments, which means this is not satisfiable. Right? Because we cannot get x1, x2, x3 values in a way that this evaluates to true. Right? Now suppose this was not there, suppose the last clause was not there, x3 complement was not there, then of course this would have been right. Suppose then this was not there, then this clause 5 would have been satisfiable with x1 true, x2 true, and x3 true, right? So now let me just bring it back, right? So this formula is not satisfiable. So the question of satisfiability is is a given Boolean formula satisfiable? Satisfiable means, is there an assignment of true false to the Boolean variables such that the formula evaluates to true? It can again be checked that this question is an NP. Right? Why? Because we can do something similar to what we did earlier. Right? We can non-deterministically assign x1 to be true and x1 to be false. So for each variable we non-deterministically pick true or false, right? And now within the two options we pick x2 true and x2 false, and similarly here, right? And so on, right? Maybe x3 true, x3 false, and finally we get something like, right? We get something like 2 power n possible options. Sorry. Not 2 options, let me just say computation paths. And for each path we check whether but then each computation path, let's take some path, right? So let's take some path, okay, let's take some path, something like this. Now each computation path corresponds to a certain assignment, right? Now we just have to verify that assignment path, does it satisfy the formula or not? If it satisfies, we accept. If it does not satisfy, we reject. So if there is a satisfying assignment, it is one of these 2 power n possible paths, and then that path leads to acceptance. If the formula is not satisfiable, meaning whatever you try it's not going to accept, then all paths will reject. So this is obviously an NP algorithm. And this is a non-deterministic algorithm, it's a correct algorithm, and the running time is polynomial because it takes n steps to non-deterministically assign yes or no or true or false to each of these n variables x1 to xn, and then it takes again linear time to verify. Okay, so this may linear time or maybe at most polynomial time to verify, right, depending on how the formula is structured, that whether this assignment satisfies the formula or not. Right. So I think linear time is enough. Right. So this shows that SAT is in NP. Right. Couple of further things that I want to just quickly briefly tell. So the formula that we saw here, right? This formula that we saw here, it is in this form called conjunctive normal form. Because I have an AND of things, so I have x1 and x1 complement or x2 and x2 complement or x3 and x3 complement, right? So I have an AND of things, but then so I have an AND of clauses where each clause is an OR of literals, right? So this is called conjunctive normal form. So here also I have another formula which is conjunctive normal form, where I have 3 clauses. First clause is x1 or x2 complement or x3 or x4, right? Second clause is x2 or x3 complement or x5. Third clause is x4 complement or x6. So it's like the formula can be viewed as C1 and C2 and C3. It's an AND of 3 clauses, where each clause is an OR of literals, right? So for instance, C1 is simply x1 or x2 complement or x3 or x4. C3 is simply x4 complement or x6. So it's an AND of clauses where each clause is an OR of literals. That's called conjunctive normal form, right? Also sometimes it is abbreviated as CNF, conjunctive normal form. So I can define a language called CNF SAT. CNF SAT simply is asking if a given formula, is it satisfiable? So it is just like SAT, right? SAT is given a formula, is it satisfiable? CNF is also asking the same question, but the given formula is in CNF form, right? So this is in CNF form, right? So so there is a certain structure to the formula that is given, and then we have to determine whether it is satisfiable, right? So this is a conjunctive normal form, and you can check that this is actually satisfiable. This is in CNF set. So you can set x1 to 1, which satisfies clause 1, x1 to true, which satisfies clause 1, x2 to true, which satisfies clause 2, and let's say x4 to false, which satisfies clause 3, right? So that's enough. So this is satisfiable. So the above, let's say this is called, let me call it psi. So above psi above formula psi is in CNF set. And further, I want to make one more definition. So this is CNF set. Earlier we defined SAT. Here I want to define one more thing called 3 CNF SAT or 3 SAT, right? This is actually a special case of CNF SAT. So CNF SAT means given a formula is satisfiable and the formula is in CNF form. 3 CNF SAT is saying that it is in CNF form, but with the additional condition that each clause has exactly 3 literals. So here in the formula psi over here, right, if you see, clause 1 has 4 variables, clause 4 literals, clause 2 has 3 and clause 3 has 2. But in 3 CNF SAT, each clause must have exactly 3 literals, that is, and then we are asking whether it is satisfiable, right? So this is even further restriction on the structure of the given formula. So perhaps the hope is that maybe if the formula has a certain specific restriction or a specific format, then maybe it is easier to figure out whether it is satisfiable or not, right? Anyway, the approach that I mentioned for SAT being in NP, I can use the same approach for CNF SAT and 3 CNF SAT, right? So I can guess a certain assignment. What we are doing is we are guessing a certain assignment and then checking whether this assignment satisfies the formula. If the guessed assignment satisfies, we accept. If the guessed assignment does not satisfy, we reject. If the formula is satisfiable, one of the guesses will lead to accept. If the formula is not satisfiable, all the guesses will reject, right? So that concludes most of what I want to say. So we said what is how to measure time complexity for a non-deterministic Turing machine, right? It is the length of the longest path, and then we take over all the possible inputs of the same length, right? Then we defined n time Tn, then we defined np. Then we also talked about the P versus NP question, right? So P is a class of languages that can be decided by deterministic Turing machine in polynomial time, and NP is a class of languages that can be decided by non-deterministic Turing machines in polynomial time, right? The question is, P is clearly a subset of NP. Is it a proper subset, right? And we discussed a bit about that. And then we saw some examples. We saw subset sum, we saw 3-colorable, and we saw SAT, right? In each of these cases, when we saw that it is an NP, right, the approach was the following, right? Maybe I'll just write that here. In all the above problems, the NP approach was to guess a solution, right? We guessed a solution and then verified it. So that's an observation. Now the question is now, are all the NP solutions like this? Like if something is in NP, does it always has to be of this form, right? Or is it just that these three problems, it just happen to be of the guess and verify type, right? Are all the NP algorithms of the guess and verify type? And the answer to that we will see in the next lecture, right? So we saw what is non-deterministic Turing machines. We saw n time, we saw NP and P, we saw the P versus NP question, and then we saw that three examples, all of which had this guess and verify approach. So the question is it just that it is by accident that these three problems had the same guess and verify approach, right? So I hope it's clear what I mean by guess and verify. In all these cases, in the case of three colorability, we guessed a three coloring and checked whether this is a proper coloring. Here we guessed a subset and checked whether the subset adds up to the sum. Here we are guessing a assignment and check whether it is satisfying, right? So the question is, are all the NP algorithms of this type? The answer turns out that any NP algorithm can be converted into this type even if it is not of this type, right? But that we will see in the next lecture, and that concludes lecture number 46. This also concludes week 9, the lectures of week 9. So we completed computability theory by seeing PCP, post correspondence problem, and an application. We showed that it is undecidable to determine whether a given context-free grammar is ambiguous. Followed by we began complexity theory. We defined the classes. We began time complexity. We saw what is d time tn and time tn. We saw p. We saw np, and then we saw examples for languages that are in p and np. Right, and we'll continue to learn about p, np, and other facts and aspects of time complexity theory in the next week. So see you in week 10. Thank you.